作业，上次的作业，然后难不难？啊，那个不等式是有点难是吧？其实你看这个，你看那些不等式是吧？条件很简单，就是凸的。啊，讲一下。可以给你讲一下，不过我今天没有准备那个，明天讲好吧？明天讲一下那些不等式什么意思，然后几何意义是什么，怎么样证它们，然后实际上你还可以证出更强的不等式啊。这些不等式啊，为什么叫大家证啊？第一个是挑战一下大家的能力啊。你应该可以至少证出几个，对吧？然后有几个比较难证，有几个比较简单。所以呢，就是这个高低搭配一下，给大家一些挑战。另外呢，那些不等式在这个后半周，在星期五我们会讲到，有些不等式跟那个跟这个收敛速度有关系啊。你用那些不等式才能证明一个算法的收敛速度，才能判断，才能预测，一个算法去解决一个问题大概需要多少步。那些不等式才是关键的东西，那些不等式实际上是最基本的、最基础的一些不等式。很多人做这个所谓的 complexity analysis 啊 ，optimization complexity analysis， 其实这个追根溯源就是那些不等式，多少就是那些不等式啊，只是那些不等式的一个比较巧妙的应用而已。有的时候还不是那么巧妙，很直接的应用。所以呢，先让大家练一练，证不出来没有关系。有一些不等式确实比较难。大家通过这个机会呢，明天我再讲一下这些不等式的几何意义，然后大家应该能慢慢你就会对那些不等式熟悉一些，然后也可以证出别的东西。这作业量觉得怎么样？多还是少？还是有点多啊？那下次少一题是吧？一周少一题。OK，然后就是我看到有同学在这个网上的论坛上面问一些关于这个作业的问题，就是我是刻意不回答的，我希望就是同学们自己去讨论，然后争取一块儿把这个问题解决啊。然后这个 solutions 我们可以下次1-2天之内就会放在网上啊，作业的这个答案就会放在网上，好吧 ？OK， 然后讲一讲这节课啊。这节课到目前为止都比较理论比较难，对吧？我这花了大概1个小时多一点的时间讲应用，其他时间都是在讲理论，讲背景，讲理论。这个课的这个设计的目的是这样啊。这个设计的目的呢，就是给大家一个比较 rigorous background。我们的课目的就是过来讲理论，然后把理论跟你的 observation 结合一下。compressive sensing 有很多人做算法做 applications， 其实大家如果有兴趣的话，看一看文章，下载一些代码，下载一些数据，都可以去，很多讲的这些东西都可以去做，都可以在 MATLAB 里面做，做完了以后你可以对照这些定理，看看是不是对的。那这些定理呢？比如说这个 recovery 的定理，告诉你们为什么你们会得到那样的结果，什么时候得不到那样的结果。所以这些定理，其实这些定理很多定理有很多的这个深刻的含义，这是为什么我花这么多时间讲这些定理的原因。下面一部分等这个 recovery 今天肯定会把这个 recovery guarantees 全部讲完。讲完之后呢，从下面开始呢，我们会多注重一些算法。同样呢，我会讲很多这个算法的定理，算法的推导，然后呢会把这个计算的任务留给大家，好吧 ？OK。然后就是你们尽管在这个 Piazza 上面 post 东西 ，post complaints， 这个 comments suggestions whatever 就放在这个post 在这个 Piazza.com 上面，我是看的，基本上我手机上就可以看，有的时候可能没有时间回或者刻意不回，不过我肯定是看到了。OK， 我们把上节课上周五讲的东西很快的复习一下啊。上周五就是无非是在解决这样的一个问题啊。Can I trust my model to return a intended sparse quantity? Can I trust my model? This is the most important thing. So if someday you sit down and write a new optimization model, whatever model you're talking about, the first thing you always have to ask is, can I trust this model to give me what I want? Okay? No, that's the most important question. All right, but it turns out there's all kind of it turns out there's all kinds of guarantees, and we have to understand what are differences between these guarantees. There are different conditions. There are weaker conditions and stronger conditions, and there are the stronger results and weaker results. So you have to differentiate these results. Hopefully some of these start to make sense for you. Alright, so we talked about spark. Spark is a combinatorial property of a matrix. It's the least number of columns that's matrix. This matrix, the least number of columns taken from the matrix that are linearly dependent. So have you seen the lecture notes with this part? The notes part. Oh, by the way, who's gonna take the note? You again? All right. Okay. All right. Great. Okay. So by the way, if you go to pieta.com, go to resources, you're gonna see the version of this slide with the notes. The notes he put in and I modified. All right. Okay. So Spark is the least number of columns that are linearly dependent, and the notes actually explains why it takes a lot of time. You will have to basically go through all possible combinations of columns in order to find the spark. Now, spark is something difficult to find. All right. But spark is pretty generous. Spark basically can go up to square root of n. Can go up to m. M is the number of rows of this matrix. Okay. Something about spark in general. Okay. Now, I pretty much give these spark and coherence in a timely order, in the order where these concepts are introduced in the history. About 20 years ago, people started to do coherence. The reason they do coherence is it's easier to calculate. All right. So if this mutual coherence, if this coherence is 0, this matrices are orthogonal. Orthogonal matrix is very simple to invert, for example. And there's a relationship between the difficult to compute quantity spark and the easy to compute quantity coherence. There's an inequality, and this inequality is proven using Gauss-Jordan's circle theorem. The notes will actually explain something. All right. Question?
I think the third bullet should be principal minor. The B should be principal minor.
Principal minor. All right. So I should put principal. Okay. I'll try to correct that. All right, thank you. All right. So you have this inequality, which is good. You see now it takes about 10 years for people to realize this inequality, which is very simple to prove. All right. So don't think that the inequalities or like new results are difficult to obtain. It's whether you want to try or not. Basically, this is 10 years, exactly 10 years before this inequality was introduced. You have the concept, then you have the inequality here. Okay. So and this inequality is not really difficult to prove. You just need to sit down, maybe think for about 1 hour, and you can get this proof. So in research, what's difficult? What's most difficult is not to give you a theorem and ask you to come up with a proof. It's come up with a guess of this inequality. All right. So if you sit down and say there might be a relation between spark and coherence, you're like halfway towards success. Okay. All right. So then we compare this to two ways of bound, and the bottom line is when these two inequalities, when your vector x is sufficiently sparse, then it will be the unique sparsest solution to the linear system of equations. This solution will be the sparsest. Any other solution to the set of equations will not be as sparse as x. All right. Okay. Now, and then, actually from the same paper, they realize this stronger condition using coherence not only guarantees spark, but also allows you to recover X using L1 norm. Now, this is a milestone in the following sense. Okay, so you're going to ask a question: when people start to realize minimizing L1 going to give you sparse solution? Long time ago, at least 20 years before this paper. All right. So because people know the geometry, right? So you see the L1 norm ball, the level set, it has sharp boundaries. Right? So people know that. But before this result, there's no any result that shows you that L1 going to give you sparse solutions. Right, so this is a milestone. And lots of people don't talk about this result, but this is a milestone. And this is basically the first time somebody ever sit down and tell you what you guess is true, at least under this condition. So under this condition, you minimize L1, you get the sparsest solution. But the problem is it only allows the sparsity go up to square root of n. We want it to be larger. Right, so we have to introduce more conditions, new conditions. Another set of conditions is null space. It's pretty rudimentary, but a bunch of inequalities. I skipped all of these. I can tell you the bottom line. Bottom line is if you want to use L1 to recover all possible k sparse solutions, not a single one missing, from the measurements, then you have to have null space property. It's if and only if property. So in other words, if somebody sit down and want to work out a universal recovery conditions, they have to start from null space property. Okay? Because this is if and only if for all k sparse recovery. Alright, so move, lots of geometry, lots of theorems, some comments. And the comments basically said it's actually also necessary for stable universal recovery. If your x naught is not exactly sparse but approximately sparse. Approximately sparse means if you truncate at k, you still have a tail. When you truncate at k's largest entry, it still has a tail. This is the tail size, the size of the tail. This tail size is bounded by if you want to have any decoder, any kind of algorithm, any kind of model that returns you a solution that's bounded by the tail size, then you have to have the null space property up to some constant c. I think it's probably the same c. I don't exactly recall, but I put it there, probably the same c. Alright. So essentially null space property is required. And by the way, null space property, you have to read the notes. Null space property means you write down, you take a vector, any non-zero vector from null space, and then you look at where are the energies of this vector. I measure energies in L1. You look at where are the energies in this vector. It tells you the energies cannot concentrate on any small set. You take any small set, no more than 2k components. The energy has to be less than the rest of the energy times constant. In other words, energy cannot concentrate on a small set. If it concentrates over there, I can always find some kind of k-sparse vectors you cannot recover. Okay, so that's the meaning. So now we move to restricted isometry principle. Property, restricted isometry property. There's nice picture here I show here in the notes, but not in this definition. But this definition basically tells you that it almost acts as an orthonormal matrix with regard to sparse vectors. It's orthonormal it's almost orthonormal with respect to all S sparse vectors. This is RIP. Under some RIP conditions, you can guarantee that you get a unique L1 recovery. And so this condition is sufficient but not necessary. This condition is sufficient for L1 unique recovery, but not necessary. It's stronger than what you need. Alright. There are some. Why do we talk about RIP? That's because the null space property is in general very difficult to check. The strict isometry property is easier to check for random matrices. There are some kind of random matrices. You just sample those matrices. For example, you want to sample this kind of matrix. All you need to do is in MATLAB, you can do A equals rand n m comma n, and you want to scale it. So I do this in order so that the columns will have unit norm in expectation. So what you do is divide it by square root of n. So this is how you would come up with a matrix in MATLAB that satisfy RIP with high probability. And just do that. You can also do the following. There are lots of matrices constructed randomly that satisfy RIP. Okay. So by the way, if you guys have interest in something called concentration measures, which is an important phenomenon, you will have to, if you study computation, if you study any randomized algorithm, big data algorithm, you will have to learn concentration measures, because it's not just a phenomenon. It's not just a concept in statistics. It's a very important tool in computation. This basically tells you it's something like central limit theorem. If you collect lots of numbers, don't make it so too complicated. Let's call it the law of large numbers. If you collect enough number of numbers and take the average will, if you sample enough number of numbers and take the average, that average will equal to the mean of the distribution. All right. It means that when you sample lots of things, it tend to be clustered in the center. Concentration measures actually tell you how to control the tails. It tells you, and this proof is actually, with overwhelming probability. This concentration measures will actually characterize how much probability when this RIP fails to hold. Well, I'm probably not going to talk too much more because it's out of the scope of this course. All right. So we also talked about coherence, did we? So we started coherence. All right. Coherence is when you do this kind of problem. Minimize, let's say, you minimize alpha, you minimize the coefficients subject to A times psi alpha equals B. Alright, so this is your signal X, and this is your sensing matrix. If your sensing matrix A is a downsample of a bigger matrix called phi. Downsample bigger matrix called phi. Now it turns out whether this model will recover the true signal kind of depend on the properties between phi and psi. Okay. And the properties require they to be almost, I wouldn't say orthogonal, they require them to be incoherent. Here's the reason. Let's suppose phi is given. And then you take psi equals phi. Probably I want a phi transpose or something. Phi transpose. Okay. Let me see. Should I use phi or phi transpose? Okay, sorry. This is phi transpose. Okay, so according to the slides, this is phi transpose. This is okay. So I basically take the basis, just the same as phi. Therefore, the coherence will be the worst. They're the same, right? They're the same. Everything inner product is itself. So this is square root of n. All right. So it's the worst coherence. What will happen? Now I know alpha is sparse. Also, they are also normal. Okay, they are also normal. I know alpha is sparse. So let me write down the system. So it's a sparse vector with there are some non-zeros somewhere. All the other places are zero. All right. This is alpha. A is just some rows of phi transpose. Alright, so this is some downsampled phi trans. This is some downsampled. Some people write it like a phi transpose and downsample. But let me write it in a different way. Let me use a projection matrix. Projection matrix will project phi transpose into a few rows of it. Right. This, you can think it as a selection matrix, a row selection matrix. You select just a few rows out of phi transpose, and then here is psi. Right. So this is the measurement B. Now, when they are equal, and these matrices are so normal, this guy is identity. Okay. So you basically did a p times alpha. So the sampling is p times alpha. P is the selection matrix. So if you really wonder what p looks like, p looks like this. P looks like every row will have exactly one number called 1 somewhere. Alright. So this matrix will select basically 5 rows of phi transpose. Alright. It will select 5 rows. Everything else is 0. Everything else is 0. So that's a selection matrix. Because this guy's identity, it cancels. So it becomes P just select some of the entries here. You're not doing compressive sensing. You're doing like a traditional, like a downsampling. So you're downsample alpha. But if your P does not downsample the non-zeros, if some non-zero is missing from the downsample, it's not sampled, then you're going to forever missing this number. Right. First, suppose you have to recover. No, you have to recover alpha, which means you have to recover all the non-zeros and their locations. Suppose you use phi transpose and psi and they equal, so they cancel to identity. And P is a downsample. So what you sample here in B are just pick some entries of alpha and put them in B. But if you miss this particular entry, you're not going to recover that. You miss it forever. There's no information about this entry, for example. Therefore, you will have to know the non-zero and non-zero positions, and have to include these positions in the downsample. If you miss one, you can lose it forever. Right. But this is not possible before you know the signal. If you don't know X, you don't know alpha. You don't know where are the non-zeros. So unless you sample, sorry about that. But you don't know where are the non-zeros. So in other words, you can't downsample. You have to sample everything. You miss one, you have a chance of missing this entire signal alpha. Alright. So which means if this thing is square root of n, this thing reaches its maximum possible value. You can't do compressive sensing. You can't compress. But when this thing is near its minimum, which means that this matrix, when they multiply together, it looks like a matrix where almost every entry is similar, has similar numbers and they roughly equal to 1 over square root of n. Right? So these numbers will be total. These numbers, none of these numbers will be 0. So it's a mixture of all the components. And then you downsample, every bit, every number in B will encode all the non-zeros somewhere, somehow, right? Which allows you to recover X. Okay, so this is the reason why we want a small coherence. And by the way, there are a bunch of matrices that give you small coherence. Okay. All right, so this actually tells you how to design a sensing system. Now, usually, signal is not what you can design, right? So this guy, this is the dictionary that makes a signal sparse is given. Psi is given. You will have some freedom to design A. In other words, design phi transpose. You should design the phi that are maximally incoherent with psi. Okay? So if psi is an identity, try to make it something like a frequency. If psi is frequency, just take identity matrix here. Right? So because frequency domain and the spatial domain are maximally incoherent. Right? Okay, so this is the theorem that turns out it tells you how many samples you have to do. If this is at its maximum, this m is at least n. Okay. All right. So now we move to robust recovery. When we move to robust recovery, we do the following. We're going to look at nearly sparse signals. We're going to look at measurement noise, and sometimes both in one problem. And the goal is no longer to exactly recover the signal, because we're basically taking fewer measurements than compared to the information. So basically, when there's noise is unknown, and when you consider nearly sparse signals, the signal can be non-sparse. Every entry of such signal is non-zero, so it encodes lots of information. But we seek the following: we're going to do a recovery so that you capture the most important information in the sparse signal. It's called robust recovery. All right. So here's one theorem. Let's consider a sparse vector x. So x is exactly sparse, and we take noisy compressive sensing measurements with unknown noise. We only know the noise is bounded, has a bounded magnitude. The amount of total noise is the energy of the noise is bounded by epsilon. And then we naturally use this model to recover x, because we no longer require ax equals b. Now if you do require ax equals b, you won't be able to get a sparse solution. Okay, so you do this. Now what can you say about this? Assume some bound on the RIP constants. You can get this kind of results. The solution of this model minus the true online signal, the 2 norm, that's the difference 2 norm. The energy of the difference is less than or equal to some constant times the energy of noise. So basically you magnify noise by a constant. If there's a certain amount of noise, epsilon amount of noise in the measurements, you magnify it by a factor of c. In practice, the c is not that big. It's about 7 or 8 at most. Okay. So this is basically tells you if your matrix is good enough, if your sensing matrix is good enough to give you RIP, then this encoding and decoding process does almost as good as a traditional sensing. Because even if I tell you where are the non-zeros, even if I tell you, you should not look at lots of the zeros, you only look at certain columns, certain entries of x. Even if I tell you that, you won't be able to do better than epsilon. Epsilon is the amount of noise energy introduced to the system, therefore your solution will definitely have this noise. Now when you do sparse optimization, lose a little bit. The little bit is a fraction c. It's not like n to the power of something, it's just a constant. This constant is independent of the signal dimension. So that's the important thing. And there's a proof sketch. Do I want to go through that? Okay, I think I can go through that. It's very simple. So this is what you do. You let E denote the error. So E is the error. We want to bound the noise of bound the energy of E. You're going to take the largest 2k entries of X. Largest 2k entries of X. Okay, one thing I want to mention is the support of X star and the support of X may be different. Sometimes you may not exactly recover all the non-zero position. They can be actually different. Right? That's why we picked the largest 2k of X. Then noise E, you're going to be able to show that the air energy is bounded by a constant times the air energy on the largest 2k entries of X. All right. So why is that? This comes from the null space property essentially. Okay, RIP guarantees null space property. RIP is stronger in general. Is a stronger condition than null space. Therefore, RIP give you this RIP bound give you null space property. It comes from here. Right. Now, but this is one norm constraint. This is two norm constraints. And different people have worked on this constant C1. You can be lazy and come up with pretty big C1, very easy, in maybe a few seconds, or you can be very careful and working all day to come up with better C1. All right, but basically this C1 is constant depending on K and these bounds. Now but this is a small, very small vector, right? This vector has up to 2k non-zeros. Therefore, if you put an A here, right, put an A here, it comes from the restricted isometry principle, because there are only 2k energy here. All right. Okay. So you're going to have this bound following from RIP, and lastly this bound, and this bound actually follows from this, from this and that. All right. So if you compare the original signal times A to B, the difference is up to epsilon. The difference is Z. The difference has up to epsilon. And you compare a solution, any solution of this one, it's feasible. So that solution will have a different distance to B up to epsilon. Therefore, this guy is actually bounded by this two norm bounded by 2 epsilon. So this norm is bounded by 2 epsilon. So this is, and essentially it's this simple idea. Following this inequality, you're going to be able to show a bound like this, except that you're going to use different tricks to come up with C1, C2. This C is simple. All right. So roughly, it's this proof. All right. So what's more important is how do we read this proof? How do we read the theorem? First thing, this result is universal for all k spars. It's more general than exact recovery also. Let's say if you make no noise, you don't introduce any noise to the measurements, then this guy is 0, epsilon is 0. So you actually have exact recovery. So it's a more general result than exact recovery. And as I said, the error bound is order optimal. You can't improve. You can't, for example, put a square root there, because even if you know the support, I'll tell you where the non-zeros are, and then you're going to use these squares. These squares will be optimal in case you have a Gaussian noise and know where the support. So even if I give you the support, you do least squares, you're gonna give you something like a C prime epsilon at best. C prime is related to the condition number of A. All right. C prime will be related to the condition number of A. It's not epsilon. It's C prime epsilon. Okay. In other words, you do comparisons and get X star. X star is almost as good as if you know where the largest k entries are and directly measure them. Okay. Now let's move to an even stronger recovery result. So at this moment, in this assumption, in this slide, so not only you have noise in the measurements, you actually have noise in the original signal. Xk is the signal that keeps the largest k entries of x. So xk is the vector formed with the largest k entries of x. So you consider something's k sparse plus some error. Of course, you're going to hope the w to be small. Recall that. Remember, like in the first lecture, in the second lecture, you see something like this, right? You see something like this, and these are the coefficients of an image, dictionary coefficient of image. So if you have a truncation k here, and all the rest is 0, this is xk, and here this part is called w. Okay. We can recover w. Actually, w will make things worse, but it's not much worse. So this tells you if you solve this model in the previous page, and you're going to get a solution x star that satisfies this. So again, you're going to have a constant times the noise, and you're going to have another constant times the tail size. This is the sigma k thing. The tail size over square root of n. Now this is just scaling. If you want to, if you can actually make it 2 norm and without the square root of k. So this is just scaling. All right, don't worry about the square root of k. All right. The proof sketch is very similar to the previous page, except that you have to consider something a little extra. Remember, we used this null space constant. We use this null space inequality. Right. This is. But now, because you don't have k-sparse vectors, you will have to consider this part. So this part is w. This is the w energy. So you're gonna have this inequality, except you have a plus 2 w1 norm here. You're gonna have little thing extra here. Everything else is the same. All right. So why do we care about this result? So this is the bound. This is the bound. It turns out this bound. We know that this part is order optimal. This noise part is order optimal. Is this part order optimal? In other words, are there some kind of energies? Are there some kind of signals on which I can't do better than this? Is this tight? It turns out it is also tight. The type of signal you consider is power law decay signal. It's power law decay signal like this. Looks like it. It's constant. This is just a scaling, so you can ignore this constant. Basically, the signal decays like a I to the negative r. R is some constant. R is some kind of power. I is I's largest entry. So in other words, if this is k, the signal is k to the minus r. So this point is k to the minus r. If you increase k, the signal will be smaller. And this kind of signal is called power law decay signals. There are lots of natural signals following power law decays. Alright. Now, when you have power law decay signals, let's compute this tail size. Now, the standard trick. If I ask you to do this series, you may have trouble computing the sum. Right? I'm computing the tail size using this series. You can relax it into an integration, to integral, and then take the integration. You're gonna get this bound. Okay, you get what I'm saying? Right, so if you have so basically what you have is a bunch of numbers. You have to add up, right? You have to add up. Don't do this. Do a upper bound, and then do an integration and integrate this part. Right. Use a standard trick, integrate. All right. So you get this bound. Then let's compute this. This is what? This is C1. So this part is C1, some constant times. I ignore the constant. So some constant times k to the power of minus r plus 1/2. All right. There's nothing. There's nothing difficult here. It's just a standard calculation. for parallel decaying signals. Okay. Now, even if I tell you where are the non-zeros, and even if I recover exactly the largest k entries exactly, all right, but this won't happen. But even if this happens, even if this happens, the bound of the difference, the energy of the difference will be less than or equal to some, if you calculate this, this is probably some other constant times k to the same order. So in other words, even if I tell you where are the largest non-zeros, you just ignore the tails. The tail has this size, right? Which basically says this bound cannot be improved, at least on parallel decaying signals. And this is a universal bound. This is the bound for any signals. This is a universal bound. Therefore, you cannot improve this bound. Right? So come now, the conclusion: the bound cannot be fundamentally improved. You may be able to improve the constants, but not this order. Now, when people come up with this bound, they just sit down and say, "Okay, I don't care anything more," and that's it. All right. So this is L1 recovery. And this is basically this kind of bound is strongest, almost like strongest universal results for L1 recovery. It considers everything. It considers noise in the measurements, considers noise in the signals, and you get that bound. All right. So, but it turns out some mathematicians don't stop there. They did a very interesting thing. This set of mathematicians is called information theoreticians. Information theoreticians. All right, so they did a crazy thing in my mind. So I would never think about doing this. Okay. So they asked the following question: is there any encoding-decoding pairs? Means the method. All right. Is there any encoding-decoding method that can do fundamentally better than Gaussian A and L1 minimization? Again, I use Gaussian A because Gaussian A has this RIP property. Is there any other method that can do fundamentally better than this? In other words, what do I mean by fundamentally? I ignore constants. I look at the orders. Is there some other method that can guarantee to do better than L1 minimization? All right, so this English sentence translated into mathematics is the following question. Does there exist an encoder-decoder pair? A is the encoder. A is the sensing matrix here, and delta is a decoder. Is any kind of decoder in the world, such that after you decode the measurements is A times X. You decode the measurements compared to the original signal, will have an energy less than or equal to O. Big O is some constant times K, 1 over K squared times the tail size. This is the sigma K is just this. Is exactly the same. Okay, I forgot to define it. That holds for K larger than this. What is that? That is what you need. How many measurements? Or let me see. So basically, if you have RIP, you have a good recovery. You have stable recovery. All right, stable recovery. So what kind of matrix can have RIP? Random matrix. Right? Many random matrix, especially Gaussian matrix. Okay. Now, what condition I have to put on these matrices? Well, this matrix will have to have m rows and n columns, but m have to be greater than or equal to some constant times k times log n over k, where k is a sparsity. Or if you give me m, give me n, give me a specific random matrix, what kind of sparse signal can I recover? Those stable recover signal will have a non-zero, number of non-zero k less than or equal to an order, it's m divided by log n over n. Alright? It's exactly the same thing. These two bounds are the same thing. Okay? So, can I basically, can I use a secret decoder so that I can recover signals with more non-zeros than what the Gaussian and L1 does? All right. Can I use a magic matrix A, non-Gaussian maybe, and use a magic recovery method so that I can recover sparse signals with more than these number of non-zeros that do better than Gaussian? All right. So A can be any matrix, delta can be any decoder, tractable, computationally tractable or not. This is a pretty crazy thing. Now, if I was given this question, I'd probably have no idea to do it. But it turns out it's just maybe 1 or 2 pages. You can actually see the answer is no. There's nothing better. All right. Okay. So this is the fundamental thing. All right, so this mathematics can be turned into this crazy equation. Right? So mathematicians enjoyed writing down some equations that really translate to long English. Right? This is very short mathematics. This tells you the following. Okay. Capital K is a set of k-sparse signals. You're only looking at k-sparse signals. All right. So K is the bound. And so you're gonna if you ignore in Feynman. If you ignore in Feynman, then everything here will have a fixed delta and fixed A. All right. And I'm looking for a k-sparse signal that gives me the worst bound. So once you fix delta and once you fix the encoder and decoder, I'm looking for a k-sparse signal that gives me the maximum bound. And I want this maximum bound to be minimized by choosing a secret A and secret delta. So I'm going to do in Feynman over encoder and decoder. Okay. And this is the error. And there's something called Gelfand width, and defined this way. It's defined like this. There is a let's say a subspace. There is a set. There is a subspace. Co-dimension means if this guy has dimension R, co-dimension is n minus R. All right. Co-dimension means company dimension. So co-dimension Y less than or equal to n. All right, so you're gonna look for a vector in the intersection of k-sparse, up to k entries and the subspace, looking for any vector H in this intersection of two subspaces with maximum energy, and then looking for a subspace with codimension a little more than m that minimizes this maximum energy. This is called the Gelfand width. It's used in many places, and these three people. They are all mathematicians. These three people tell you, well, if you set this is of course true. This is of course true. K is k-sparse signal. Set of k-sparse signals. I mean, this is true, and this is also true. If you put any two k-sparse signal, any this k-sparse vector plus another k-sparse vector, of course, is less than or equal to some 2k plus vectors. All right. Then it turned out. It's not a really long proof. It turns out this quantity is related to the Gelfand width up to a certain constant. This constant is this. Right. So in other words, this question, the answer to this mathematical question is bounded by something so-called Gelfand width. All right. Now, some people have proven. Russians have actually told you what these are, if these are random. Right? The Russians actually have told you that, actually not for random, but this time for L1. They've told you that if for K, for this specific K, with L1 norm less than 1, then, okay, I made a mistake. This is for Gelfand width for K equal to L1 ball. Sorry, so I thought the K was the k-sparse signals. So this is for K equal to L1 norm ball. And then this quantity can be calculated. The quantity is actually bounded by basically this order times the lower bound and upper bound. In the same order multiply it by a lower bound, upper bound. So it's basically off this order. Okay. Well, this means this quantity is of that order, of the same order, because this quantity is bounded by this Gelfand width and some constant times the Gelfand width. So this quantity is of the order. Some mathematicians use approximate equal, means it's equal to the order of something. Well, it means this. It means this error equals this. If we want any secret encoder and decoder pair with a bound, with a stability bound like this, and you normalize this vector. Have unit 1 norm. You will get exact the same bound. Let's see. So you normalize over x1, normalize over x, you're going to give you this constant. This is the exact same constant that you get with Gaussian and L1. So which means you can find better encoder and decoder pairs, secret better encoder decoder pairs that does fundamentally better than Gaussian and L1. All right, in terms of stability. If you want a stable recovery, you can't do much better than using a Gaussian random matrix that gives you RIP and L1 recovery. Okay. Now this does not mean, by the way, you cannot do better in practice than this. In practice, you may be able to do better than this order if you have extra information beyond sparsity about x. If you know, for example, if you know x has certain form, it can only come out of certain small subsets, you can actually do better than this. But otherwise, if you only know sparsity, you can't do better than this. Right? This is what it tells you. Right? So I'm going to give you a break. So next class, I'm going to tell you, I'm going to switch to a different set of slides called dual certificate. So next class we're going to start this. This is more related to optimization, right, rather than information theory. Okay. All right. So let's have a 10-minute break.